Something extraordinary is happening right now above our heads, and it might finally explain the most famous mystery in the history of space exploration. For 47 years, scientists have been haunted by a 72-second radio signal, so powerful and so perfectly engineered that the astronomer who discovered it could only write one word in red ink across the data. Now, hurtling toward us through the darkness of space, comes an object that shouldn't exist. An interstellar visitor with chemistry that defies every model we have of how planets form, arriving from the exact same patch of sky where that impossible signal originated nearly half a century ago. This isn't coincidence. This is contact. The story begins on a sweltering August night in 1977, when most of America was asleep and unaware that human history was about to change. Deep in the Ohio countryside, a massive radio telescope called Big Ear was conducting its nightly sweep of the heavens, searching for whispers of intelligence among the stars. The telescope wasn't much to look at, essentially a giant metal trough stretching the length of 3 football fields. But on this particular night, it captured something that would baffle scientists for decades to come. At exactly 11:16 p.m., as the constellation Sagittarius drifted through the telescope's field of view, the receivers registered a signal unlike anything in their databases. It wasn't the random static of cosmic background radiation or the predictable pulses of distant stars. This was something else entirely. A narrowband transmission centered at 120.45 MHz, climbing steadily in intensity before fading away exactly as expected for an astronomical source tracked by the telescope's beam. But here's what made it extraordinary. The signal was incredibly strong, roughly 30 times brighter than typical background noise. In the world of radio astronomy, that's not a whisper, that's a Days later, volunteer astronomer Jerry Amon was reviewing the computer printouts from that night's observations when his eyes stopped at something impossible. The Big Ear's primitive computers converted radio intensity into alphanumeric characters, with higher numbers and letters representing stronger signals. As Amon scanned the rows of 1s and 2s representing cosmic silence, he found a sequence that climbed and fell in perfect symmetry. The pattern exactly matched what you'd expect from a point source in space, tracked by the telescope as Earth rotated. Amon grabbed a red pen and circled the anomalous data. In the margin, he scrawled a single word that would echo through decades of scientific investigation. Wow! The signal's characteristics read like a textbook example of what researchers had long theorized they might find if extraterrestrial intelligence was trying to communicate with us. It was narrowband, suggesting an artificial origin, since nature rarely produces such precisely defined frequencies. It appeared to come from a fixed point in space rather than moving like a satellite or aircraft. Most intriguingly, it fell almost exactly on the hydrogen line frequency at 120 MHz, the precise wavelength that many scientists had identified as the universe's natural hailing frequency. This frequency is special for a profound reason. Throughout the cosmos, hydrogen atoms occasionally flip their magnetic orientation, releasing energy at exactly 1420-35 MHz. It's a universal constant written into the fundamental physics of the universe itself. Any civilization that discovers radio astronomy will inevitably find this frequency. If you wanted to send a message that would be understood across interstellar distances by any technologically advanced species, this is exactly the wavelength you would choose. The fact that the WOW signal appeared at this frequency seemed to validate decades of theoretical work about how extraterrestrial civilizations might attempt to communicate. But then something frustrating happened. Nothing. The Ohio State University team immediately repositioned other telescopes toward the suspected source region and began intensive searches. They found cosmic silence. The signal had vanished as mysteriously as it had appeared, leaving behind only that single printout and a growing sense that they had witnessed something unprecedented. This began what would become one of the most extensive follow-up campaigns in the history of the search for extraterrestrial intelligence. Over the following years, dozens of radio telescopes around the world pointed toward the WOW signal's suspected location. The Very Large Array, Arecibo, Parkes, and countless others joined the hunt. Some searched continuously, others intermittently. All came up empty. The signal's non-repeating nature presented researchers with a fundamental challenge. How do you verify something that happened once and never again? How do you distinguish between a genuine extraterrestrial message and an unknown natural phenomenon? As years turned to decades, various explanations emerged. Some researchers suggested it might represent a previously unknown class of astronomical object, perhaps a neutron star undergoing a rare magnetic field reconfiguration, or a hydrogen cloud illuminated by some distant energetic event. Others proposed more exotic scenarios involving collapsed stars, black holes, or interstellar mazes triggered by cosmic collisions. One particularly contentious explanation emerged, suggesting the signal might have originated from comets carrying hydrogen clouds, but this hypothesis was quickly dismissed by experts who pointed out fundamental flaws in the theory. Recent reanalysis using improved data processing techniques has shed new light on the signal's properties. Scientists have narrowed its possible location to a region only about 8 arc-minutes across, roughly 1/4 the apparent diameter of the full moon. They've confirmed its extraordinary intensity and identified subtle patterns in surrounding data that had gone unnoticed for decades. Most significantly, they found evidence consistent with what astronomers call a hydrogen maser, a cosmic radio laser created when interstellar gas becomes excited by nearby energy sources. This maser hypothesis has emerged as the leading natural explanation for the WOW signal, but even it carries profound implications. If the signal was indeed a hydrogen maser, it represents a type of astrophysical event that has never been observed before or since. The timing would be remarkable, occurring at exactly the frequency where humans were conducting their most intensive searches for extraterrestrial intelligence. The location would be significant, originating from the same region of sky that has now produced our most mysterious interstellar visitor. Fast forward to July 1st, 2025. While most of the world slept, an automated telescope system in Chile's Atacama Desert was methodically photographing the night sky, searching for asteroids that might pose threats to Earth. The ATLAS survey had been conducting this vigil for years, cataloguing the movements of countless rocks orbiting peacefully within our solar system's gravitational embrace. But on this particular night, the cameras captured something extraordinary. Moving against the background stars at a speed that immediately caught the attention of automated detection algorithms was an object that clearly didn't belong to our solar system family. Its trajectory screamed outsider, a hyperbolic path that curved around our sun not because it was gravitationally bound, but because it was merely a temporary visitor, bent briefly from its original course before continuing into the darkness between stars. The Discovery team quickly recognized they had found something historically significant. Preliminary orbital calculations revealed an eccentricity exceeding 1.0, the mathematical signature of an interstellar wanderer. They designated it 3IATLAS, the third confirmed interstellar object to visit our solar system. Unlike Oumuamua, which had been discovered after its closest approach to the Sun and was already racing back toward interstellar space, 3IATLAS was still inbound, offering months of detailed observation opportunities. But as data accumulated, a picture emerged that challenged every expectation about what interstellar comets should look like. When the James Webb Space Telescope turned its unprecedented infrared vision toward 3IATLAS, it revealed a cometary atmosphere dominated by carbon dioxide in concentrations that defied explanation. Most comets native to our solar system exhibit the opposite pattern, with water vapor typically outshining carbon dioxide by factors of 10 or more. But 3IATLAS displayed a carbon dioxide to water ratio of approximately 8:1, suggesting formation conditions radically different from anything in our cosmic neighborhood. The Hubble Space Telescope contributed equally puzzling data. Its observations placed an upper limit of approximately 5.6 kilometers on the nucleus diameter, with some analyses suggesting the object might be significantly smaller. Yet despite its modest dimensions, 3IATLAS was producing cometary activity comparable to objects many times its size. The ghostly atmosphere of gas and dust surrounding the nucleus expanded to hundreds of thousands of kilometers in diameter, while the tail stretched millions of kilometers behind the object. This apparent overperformance sparked intense debate among cometary physicists. Spectroscopic observations added another layer of mystery. When ground-based telescopes analyzed the light emitted by 3IATLAS's coma, they detected strong emission lines from nickel atoms, a common finding in many comets that typically indicates metallic particles being vaporized by solar radiation. But conspicuously absent were corresponding emission lines from iron, nickel's frequent companion in cosmic environments. This selective metal emission puzzled astronomers familiar with typical cometary chemistry. The object's orbital characteristics contributed additional intrigue. 3IATLAS was approaching on a retrograde trajectory, moving in the opposite direction from most solar system objects, with an orbital inclination of only about 5 degrees relative to the ecliptic plane. While retrograde motion isn't impossible for natural objects, it's statistically uncommon. Finding an interstellar visitor moving retrograde but nearly coplanar with our solar system represented another coincidence in an already coincidence-rich discovery. But here's where the story becomes truly extraordinary. 3IATLAS was approaching our solar system from the general direction of Sagittarius, the same constellation where the WOW signal had originated 48 years earlier. NASA's trajectory analysis confirmed what preliminary observations had suggested. The object's radiant, the point on the celestial sphere from which it appeared to originate, fell within the same broad region of sky where that famous radio transmission had been detected 4 decades ago. The significance of this directional correlation depends on understanding what Sagittarius represents in cosmic terms. When we look toward this constellation, we're not just gazing at random star patterns, we're peering directly into the gravitational and energetic heart of our galaxy, where star densities reach levels unimaginable in our local cosmic neighborhood. The galactic center environment presents both opportunities and challenges for potential extraterrestrial civilization. Dense stellar populations could support vast communication networks, but intense radiation and gravitational disruptions might make stable planetary systems difficult to maintain. From a strategic perspective, the galactic center region represents an obvious target for interstellar communication. If advanced civilizations wanted to establish galaxy-wide networks, placing broadcast facilities near the galactic center would maximize coverage while minimizing energy requirements. This strategic logic influenced early search strategies and continues to shape modern programs. The timing of these events creates perhaps the most compelling aspect of the entire mystery. If 3IATLAS has been wandering through interstellar space for millions of years since its ejection from some distant planetary system, what are the odds it would arrive during the same historical epoch when humans developed radio astronomy and happened to detect an unexplained signal from the same general direction? The universe has existed for 30. Human civilization has possessed radio technology for less than 150 years. The probability that two genuinely unrelated phenomena would converge on our planet during this cosmically brief window seems vanishingly small. Various explanations have emerged to account for these correlations. Conservative researchers emphasize that Sagittarius covers a vast area of sky, roughly equivalent to 600 full moons arranged in a grid pattern. Finding two unusual objects within the same constellation might not be particularly surprising from a statistical perspective. They point to the object's fundamentally comet-like behavior, its development of coma and tail, its response to solar heating, and its purely gravitational trajectory as evidence of natural origin. But other researchers find these conventional explanations inadequate. Harvard astrophysicist Avi Loeb, who previously argued that Oumuamua might represent alien technology, has turned his attention to 3IATLAS with characteristic boldness. He contends that the accumulating anomalies suggest possible artificial origin, noting that the carbon dioxide dominance could theoretically result from industrial processes rather than primordial condensation, and that the selective nickel emission might reflect manufactured materials with specific metallurgical properties. The scientific community remains divided. Critics note that extraordinary claims require extraordinary evidence, and that the observed anomalies, while unusual, remain within the bounds of what might be expected from natural objects formed in exotic environments around different types of stars. They emphasize that 3IATLAS exhibits classic cometary behavior without the kind of controlled maneuvers that would definitively indicate technological origin. Yet even skeptics acknowledge that 3IATLAS represents something genuinely unprecedented. Its combination of unusual chemistry, compact size, vigorous activity, and directional origin from the same region of sky as the WOW signal creates a pattern that stretches coincidence to uncomfortable limits. The question remains, are we witnessing random cosmic coincidence, or the first hints of something far more extraordinary? One of the most audacious hypotheses to emerge suggests we might be witnessing a coordinated interstellar communication effort, a cosmic conversation conducted across decades and light years with messages encoded not just in radio waves, but in the physical movement of objects through space itself. According to this message in motion theory, the WOW signal served as an initial announcement, a brief radio transmission designed to capture attention, while 3IATLAS represents a sophisticated follow-up message, a physical probe carrying information or instruments from its creators. The apparent 48-year delay would make perfect sense in this context. Radio waves travel at light speed, covering interstellar distances in years or decades. Physical objects, even with advanced propulsion, would require much longer transit times. The timing suggests an origin perhaps 10 to 30 light-years from Earth, close enough for radio communication, far enough to require substantial time for physical travel. This hypothesis generates specific testable predictions. We might detect structured radio emissions from 3IATLAS itself, particularly during close approaches to major planets. These transmissions might occur at frequencies related to the original WOW signal, perhaps harmonics of the hydrogen line or other mathematically significant wavelengths. The object might display non-gravitational accelerations, inconsistent with normal cometary outgassing, or reveal material compositions impossible to achieve through natural processes. As 3IATLAS continues its journey through our solar system, approaching critical encounters with Mars in October, the Sun in late October, and Earth in December, radio telescopes around the world are preparing for what may be the most intensive search for extraterrestrial intelligence in history. The Breakthrough Listen project has already begun dedicating substantial observing time to monitoring the object, while China's FAST telescope and other facilities worldwide have joined the campaign. The listening strategy focuses on the most promising observational windows. The Mars flyby in early October represents the first critical opportunity, as 3IATLAS passes within 30 million kilometers of the red planet. If the object were programmed to respond to planetary encounters, this would be the moment for initial activation. The perihelion passage in late October offers even more dramatic possibilities, as solar heating reaches maximum intensity, potentially triggering changes in behavior or revealing hidden capabilities. But perhaps the most significant window occurs during 3IATLAS's closest approach to Earth in mid-December, at approximately 270 million kilometers distance. Any signals originating from the object would reach maximum strength while minimizing Doppler effects that could complicate frequency analysis. The geometry would allow continuous monitoring by radio telescopes worldwide as Earth's rotation sweeps different facilities into optimal viewing positions. The searches will span broad spectral ranges from low-frequency radio waves through microwave and millimeter wavelengths, with special attention to the exact frequency where the WOW signal appeared. Modern signal processing algorithms can identify artificial signatures even when embedded in noise, searching for complex modulation patterns, precise frequency stability, or structured information content that would distinguish genuine extraterrestrial transmissions from natural radio sources. The technical challenges extend far beyond simple sensitivity requirements. Any genuine alien signal would likely display characteristics that distinguish it from natural sources. Doppler analysis presents particular opportunities, since 3IATLAS's motion creates predictable frequency shifts for signals originating from the object. Artificial transmissions might show additional frequency drifts designed to compensate for relative motion or encode information in changing signal characteristics. Citizen science plays an increasingly important role in these searches. Projects like SETI@Home have demonstrated the power of distributed computing for analyzing vast amounts of radio data, while amateur astronomers with sophisticated equipment contribute valuable observations. The 3IATLAS campaign provides opportunities for both professional and amateur participation in what may be humanity's most significant search for extraterrestrial intelligence. The psychological and sociological aspects deserve equal consideration alongside technical challenges. If artificial signals are detected, the discovery would trigger carefully planned verification and notification protocols developed by the international community. Independent confirmation by multiple telescopes would be required before public announcements, followed by detailed analysis to rule out terrestrial interference or natural explanations. But negative results would be equally significant, though perhaps less dramatic. The absence of detectable signals would place valuable constraints on potential alien technology, while demonstrating humanity's growing capabilities for interstellar communication monitoring. Each null result narrows the parameter space for extraterrestrial civilizations and refines our understanding of cosmic communication challenges. Beyond immediate mystery surrounding 3IATLAS and its potential connection to the WOW signal, lies a broader transformation in our understanding of the cosmic environment we inhabit. This interstellar visitor represents far more than a single anomalous object. It embodies our species' growing recognition that the universe is dynamic, interconnected, and full of wanderers carrying stories from worlds we may never directly observe. The scientific value extends into fundamental questions about planetary system formation and evolution. Every interstellar object carries within its chemistry and structure the fossil record of processes that occurred around alien suns. These serve as time capsules, preserving information about stellar environments, protoplanetary disk compositions, and mechanisms by which worlds are born. 3IATLAS's unusual carbon dioxide to water ratio provides perfect examples of this archaeological potential. In our solar system, volatile compound patterns reflect specific conditions during the Sun's formation 4.6 billion years ago. Finding an interstellar comet with dramatically different ratios suggests formation around stars with different properties, perhaps more massive, hotter, or enriched with different heavy element abundances. Modern observatory capabilities are perfectly positioned to extract maximum scientific value from this passage. The James Webb Space Telescope's infrared sensitivity allows detailed molecular emission analysis impossible with previous instruments. Hubble's high-resolution imaging provides constraints on size, shape, and rotation that inform structural models. Ground-based facilities contribute complementary capabilities through continuous tracking as the object evolves during solar encounter. The lessons learned will prove invaluable for studying future interstellar visitors, which are likely to arrive with increasing frequency as detection capabilities improve. The Legacy Survey of Space and Time, scheduled to begin operations later this decade, will dramatically expand our ability to discover approaching objects. Current estimates suggest dozens or hundreds of additional visitors might be detected over the next decade. This growing population will transform interstellar objects from individual curiosities into statistical samples that can reveal broader patterns about planetary system formation throughout the galaxy. We'll begin understanding which object types are commonly ejected during system evolution, what chemical signatures characterize formation around different stellar types, and how frequently genuine anomalies occur among interstellar wanderers. The broader implications extend into astrobiology and the search for life beyond Earth. While 3IATLAS shows no obvious signs of hosting biological activity, future visitors might carry organic compounds, complex molecules, or even preserved microorganisms from their original system. Such discoveries would provide direct evidence about chemical evolution in different cosmic environments. The potential for panspermia, life transfer between systems via natural processes, adds another dimension to interstellar object research. If microorganisms can survive extreme interstellar conditions for millions of years, then objects like 3IATLAS might serve as vectors for biological exchange across vast cosmic distances. Detecting preserved life would revolutionize our understanding of biology's cosmic distribution. Even without biological payloads, interstellar visitors provide crucial data about galactic chemical evolution over cosmic time. Objects ejected billions of years ago preserve information about stellar nucleosynthesis products, supernova enrichment patterns, and heavy element distributions from earlier galactic epochs. They serve as archived samples from environments that may no longer exist. The technological and methodological advances driven by interstellar object research benefit astronomy more broadly. Improved algorithms for detecting fast-moving objects enhance our ability to track potentially hazardous asteroids. Better spectroscopic analysis techniques advance understanding of solar system comets and asteroids. Enhanced international coordination protocols strengthen the global astronomical community's rapid response capabilities. Perhaps most importantly, studying objects like 3IATLAS forces us to confront the limitations of current knowledge, while remaining open to possibilities that stretch understanding. The object's anomalous characteristics remind us that the universe continues to surprise, challenge assumptions, and reveal phenomena we haven't yet learned to expect. As 3IATLAS continues toward its critical encounters, it carries the accumulated curiosity and technological capabilities of our entire species. Every spectrum collected, every image captured, and every measurement made contributes to humanity's expanding understanding of our shared cosmic environment. Whether the object ultimately proves to be an exotic natural comet or something more extraordinary, its passage marks a milestone in our species' cosmic maturity. The bigger picture reveals a cosmos far more dynamic and interconnected than previous generations imagined. A place where matter and perhaps life routinely travel between star systems, where every world potentially influences every other world, and where the next discovery might fundamentally transform our understanding of our place in the cosmic community. The story we've traced represents more than chronicles of unexplained phenomena. It embodies humanity's persistent refusal to accept easy answers, our willingness to pursue questions, even when they lead into uncomfortable uncertainties, and our growing confidence in investigating the cosmos with scientific rigor. Whether the correlation between the WOW signal and 3IATLAS ultimately proves meaningful or coincidental, both phenomena have already succeeded in advancing our understanding. The original transmission demonstrated that our instruments could detect powerful interstellar signals, validating search strategies and inspiring generations of researchers. It established evidence evaluation benchmarks that continue guiding responses to anomalous discoveries. The scientific process guiding these investigations exemplifies humanity's most noble intellectual traditions. We observe carefully, measure precisely, propose hypotheses, test predictions, and remain prepared to revise conclusions based on new evidence. This methodological rigor becomes particularly crucial when investigating phenomena that might represent contact with extraterrestrial intelligence. The potential implications are so profound that extraordinary care must be taken to avoid both premature conclusions and premature dismissals. We must remain open to possibilities that might transform understanding of our cosmic place while maintaining skeptical scrutiny that prevents wishful thinking from masquerading as scientific discovery. As radio telescopes worldwide prepare to listen with unprecedented sensitivity during 3IATLAS's passage, these searches represent more than attempts to validate specific hypotheses. They embody humanity's commitment to remaining alert for messages from beyond our world. The listening campaigns also serve as preparations for future opportunities, establishing standards for responding to other anomalous objects or signals. Looking forward, the coming decades promise revolutionary advances in investigating cosmic mysteries. Next-generation radio telescopes will achieve sensitivities that dwarf current capabilities, detecting much weaker signals across broader frequency ranges. The James Webb Space Telescope and successors will provide unprecedented views of exoplanet atmospheres, potentially revealing biosignatures or technosignatures in distant world compositions. But perhaps the most significant development will be the maturation of our species' cosmic perspective. Each investigation of anomalous phenomena, each null result in searches, and each discovery of exotic but natural objects contributes to growing understanding of what's possible, probable, and mysterious in our universe. The correlation between the WOW signal and 3IATLAS, whether ultimately meaningful or coincidental, has already served valuable purposes by focusing attention on evidence types needed to establish genuine connections between apparently separate phenomena. It has forced development of more rigorous statistical frameworks for evaluating cosmic coincidences, more sophisticated techniques for analyzing anomalous objects, and more careful protocols for distinguishing between natural and artificial signatures. These methodological advances will prove invaluable for future mysteries, and we can be certain such mysteries will continue emerging as observational capabilities expand. The universe has a long history of surprising us with unanticipated phenomena. From pulsars and quasars to dark matter and dark energy, each discovery has required expanding conceptual frameworks and revising understanding of physical reality. The search for extraterrestrial intelligence represents perhaps the ultimate example of this scientific adventure. Unlike other astronomical investigations focusing on physical processes or cosmic structures, these searches look for phenomena deliberately created by beings with intentions, capabilities, and motivations we can only imagine. This requires confronting profound questions about intelligence, nature, technological civilization likelihood, and interstellar communication methods. Whether we are alone in the universe remains one of the most profound questions our species has posed. The correlation between a mysterious radio signal and an enigmatic interstellar visitor provides no definitive answers, but offers something equally valuable, a framework for thinking about how such answers might eventually emerge. In the months ahead, as 3IATLAS continues its solar system journey and our instruments maintain vigilant monitoring, we carry the accumulated wisdom of generations of astronomers who dared look up and wonder what might be looking back. Their curiosity has become our inheritance. Their questions have become our quest. The next wow moment may come tomorrow, next year, or decades from now. It might arrive as a radio signal, optical flash, or visitor displaying characteristics leaving no doubt about artificial origin. When it comes, and the optimist in every scientist believes it will, we will be ready. We have built the instruments, developed protocols, and cultivated intellectual frameworks necessary to recognize, verify, and respond to extraterrestrial intelligence evidence. More importantly, we have maintained the sense of wonder and possibility that drives all great discoveries. The universe is vast, ancient, and filled with more stars than grains of sand on Earth. Among those countless suns, physics and chemistry have had billions of years to create complexity, diversity, and perhaps intelligence we can barely imagine. The cosmos keeps its secrets well, but we have proven ourselves persistent students. Whether we are alone or accompanied in this vast expanse, the search itself ennobles us, challenges us, and connects us to something larger than ourselves or our planetary home. In the end, that may be the greatest discovery of all, that we are capable of asking such questions and brave enough to seek answers wherever they might lead us in the infinite darkness between the stars. Right now, as you watch this, 3IATLAS is racing through space toward its closest encounter with Earth. Radio telescopes are listening, scientists are analyzing, and somewhere in the data being collected at this very moment might be the answer to humanity's oldest question. Are we alone? The universe is about to tell us. We just have to be ready to listen. But to truly understand the magnitude of what we might be witnessing, we need to dive deeper into the science behind these extraordinary events. The technical details of how we detect and analyze interstellar signals aren't just academic curiosities. They're the foundation upon which humanity's greatest discovery might rest. The Big Ear radio telescope that detected the WOW signal was a marvel of engineering simplicity and effectiveness. Built in 1963 at Ohio State University, it consisted of a fixed parabolic reflector measuring 110 by 70 meters, making it roughly equivalent in collecting area to a circular dish about 53 meters in diameter. What made Big Ear unique wasn't its size, but its design philosophy. Unlike steerable dishes that can point in any direction, Big Ear was fixed in place, relying on Earth's rotation to sweep its beam across the sky. This design had both advantages and disadvantages for signal detection. The advantage was continuous sky coverage. Every 24 hours, Big Ear would scan the entire visible sky, making it an ideal survey instrument for detecting unexpected signals from unknown sources. The disadvantage was limited follow-up capability. Once Earth's rotation carried a source out of the telescope's beam, astronomers had to wait a full day for another opportunity to observe it, assuming the source was still transmitting. The night of August 15, 1977, Big Ear was conducting routine observations as part of its ongoing SETI program when the unexpected happened. The telescope's receivers were monitoring a frequency band centered on the hydrogen line, specifically chosen because of its significance for potential interstellar communication. The detection equipment was surprisingly primitive by today's standards. Analog receivers feeding data to a computer system that printed results on continuous form paper using alphanumeric characters to represent signal strength. When Jerry Amon discovered the famous 6EGOJ5 sequence days later, he was looking at a representation of signal intensity over time. The number 6 represented a signal about 6 times stronger than background noise. The letter E indicated about 14 times background, Q represented 26 times, U was 30 times, J was 19 times, and the final 5 showed the signal fading back to 5 times background. This created the characteristic bell-shaped curve expected from a point source tracked by the telescope's beam. What made this pattern so remarkable wasn't just its intensity, but its precision. The signal appeared to originate from a specific location in space and maintained its frequency with extraordinary stability. Natural radio sources, such as pulsars or solar flares, typically display frequency drift, bandwidth spreading, or other characteristics that distinguish them from artificial signals. The WOW signal showed none of these natural signatures. The frequency precision was particularly striking. The signal appeared at 108.455 MHz, just 50 kHz away from the pure hydrogen line frequency. This slight offset could be explained by Doppler shift due to relative motion between Earth and the source, or it might represent deliberate frequency selection to avoid interference from natural hydrogen emissions. Either explanation suggested a level of sophistication that pushed the boundaries of what natural phenomena could produce. Modern reanalysis of the original data has revealed additional details that were invisible to 9. Advanced signal processing techniques, applied to digitized versions of the original printouts, have identified weak enhancements at nearby frequencies and times, suggesting the main signal might have been embedded within a more complex emission structure. These patterns are consistent with what astronomers might expect from a hydrogen maser undergoing rapid temporal evolution, but they're also compatible with artificial signal designs intended to convey structured information. The hydrogen maser explanation has gained considerable support among astronomers because it provides a natural mechanism for producing intense narrowband emissions at the hydrogen line frequency. Masers occur when molecules in space become excited by nearby energy sources, creating conditions analogous to cosmic radio lasers. Hydrogen masers, while rare, have been observed in star-forming regions and around evolved stars undergoing mass loss. For a hydrogen maser to explain the WOW signal, specific conditions would be required. A cloud of hydrogen gas must be illuminated by some powerful energy source, perhaps a magnetar flare, supernova shockwave, or gamma-ray burst from a distant galaxy. The radiation excites hydrogen atoms throughout the cloud, creating population inversions that amplify radio waves at the 21 centimeter frequency. As the energy pulse propagates through the cloud, different regions light up in sequence, creating a transient maser that might last minutes to hours before fading forever. This scenario accounts for several puzzling aspects of the WOW signal. It explains the precise frequency match to the hydrogen line and predicts the narrow bandwidth observed. It allows for extraordinary intensity through maser amplification, and most importantly explains why the signal never repeated. The triggering event was presumably a one-time occurrence creating temporary conditions unlikely to be duplicated. However, even this natural explanation faces challenges. Hydrogen masers powerful enough to produce the observed signal intensity would require energy inputs comparable to stellar explosions. Such events should be detectable across multiple wavelengths. Yet no corresponding X-ray bursts, gamma-ray flares, or optical transients were recorded from the WOW signal's direction around August. The absence of multi-wavelength signatures doesn't definitively rule out the maser hypothesis, but it does highlight the extraordinary nature of whatever produced that famous 72. The search techniques used to follow up on the WOW signal have evolved dramatically over the decades. Modern SETI searches employ sophisticated digital signal processing systems capable of monitoring millions of frequency channels simultaneously. They can detect signals thousands of times weaker than what big ear could register, and they can analyze signal characteristics in real time rather than waiting for post-processing analysis. Contemporary search strategies also recognize that extraterrestrial signals might not conform to human expectation. While early SETI focused on continuous wave transmissions, similar to terrestrial radio broadcasts, modern searchers look for pulsed signals, frequency hopping patterns, and complex modulation schemes that might be more efficient for interstellar communication. They monitor optical wavelength for laser communications, search for brief radio bursts that might carry compressed data, and even look for artificial modifications to stellar spectra that could indicate advanced engineering projects. The Breakthrough Listen project, launched in 2015 with $100 million in funding, represents the most comprehensive SETI search ever undertaken. Using facilities like the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, Breakthrough Listen monitors hundreds of thousands of nearby stars across a frequency range, spanning from 1 to 5. The project's data processing capabilities dwarf anything available to previous generations of SETI researchers, analyzing petabytes of observational data to identify candidate signals that merit further investigation. Yet despite these technological advances, no signal matching the characteristics of the original WOW transmission has ever been detected. This absence of similar events either supports the hydrogen maser hypothesis, suggesting we witnessed a rare natural phenomenon, or indicates that genuine extraterrestrial signals are extremely uncommon, highly directional, operating according to communication protocols we don't yet understand. The arrival of 3IATLAS has provided an unprecedented opportunity to test these various hypotheses. Unlike the ephemeral WOW signal which appeared once and vanished forever, our interstellar visitor offers months of continuous observation as it traverses our solar system. If 3IATLAS was somehow connected to the original transmission, we might expect to detect radio emissions as the object approaches key gravitational waypoints in its trajectory. The physics of interstellar travel provides crucial context for evaluating the connection between these phenomena. Even at relativistic speeds approaching the speed of light, physical objects require thousands of years to traverse the distances between nearby star systems. More realistic propulsion technologies would extend these journey times to tens of thousands or millions of years. This temporal mismatch seems to argue against any direct connection between a radio signal from 1977 and a physical object arriving in. However, alternative scenarios could reconcile these timing issues. The original signal might have been transmitted not from the object's origin point, but from somewhere along its trajectory as 3IATLAS passed through an intermediate star system. Advanced civilizations might establish relay stations throughout the galaxy, with each station programmed to announce the passage of important objects or missions. Alternatively, the signal might have originated from the destination rather than the source. If 3IATLAS were an autonomous probe dispatched toward our solar system millions of years ago, the original radio transmission might have been generated by monitoring stations within our own galactic neighborhood, announcing the probe's imminent arrival to any listening civilizations. These speculative scenarios highlight the complexity of interstellar communication strategies. Advanced civilizations would face fundamental challenges in coordinating activities across the vast scales of space and time that separate star systems. Radio signals travel at light speed, but even to nearby stars, round-trip communication times span decades. Physical objects, regardless of their propulsion systems, require far longer transit times. Under such constraints, any interstellar civilization would need to develop autonomous systems capable of operating independently for millennia or longer. Probes dispatched to distant star systems couldn't rely on real-time guidance from their creators. They would need sophisticated artificial intelligence, detailed pre-programmed instructions, and the capability to adapt to unexpected situations. This technological reality shapes our expectations for how alien probes might behave if they enter our solar system. Rather than obvious artificial structures broadcasting clearly intelligible messages, we might expect subtle reconnaissance missions designed to gather information while minimizing detection. Such probes might disguise themselves as natural objects, using camouflage technologies to avoid triggering defensive responses from potentially hostile civilizations. The selective chemistry displayed by 3IATLAS could theoretically support such camouflage scenarios. Its unusual carbon dioxide to water ratio might reflect deliberate engineering rather than natural formation processes. Industrial systems optimized for specific functions could produce waste products or exhaust gases with ratios different from those found in naturally formed comets. Similarly, the mysterious nickel emissions without corresponding iron signatures might indicate manufactured materials rather than primordial condensates. Advanced metallurgy could produce alloys or composites with properties specifically designed for interstellar travel. Materials optimized for radiation resistance, thermal management, or structural integrity under extreme conditions. The object's apparent overperformance relative to its size presents another potential indicator of artificial origin. Natural comets release volatiles at rates determined by their surface area, internal structure, and composition. An artificial object might achieve higher activity levels through engineered surfaces, internal heating systems, or deliberate material releases designed to maintain convincing cometary appearances. These speculations remain just that, speculations. The extraordinary nature of the claims requires extraordinary evidence, and current observations of 3IATLAS provide nothing approaching definitive proof of artificial origin. The object's behavior remains consistent with exotic but natural comet properties, and its unusual characteristics could result from formation in stellar environments unlike anything in our solar system. The challenge of distinguishing between highly unusual natural phenomena and potential alien technology represents one of the fundamental problems in SETI research. As our understanding of cosmic environments expands, we discover that nature is capable of producing increasingly sophisticated signals and structures. Pulsars, when first detected in 1967, seemed so precisely timed that astronomers initially labeled them LGM for little green men, before recognizing their true nature as rotating neutron stars. Fast radio bursts discovered in 2007 displayed such exotic characteristics that some researchers initially suspected technological origins. These brief, intense radio pulses seem to carry more energy than the sun produces in an entire day, compressed into millisecond duration flashes. The discovery that these bursts originated from cosmological distances and their association with magnetars and other extreme astrophysical objects eventually provided natural explanations for their extraordinary properties. The history of astronomy is filled with phenomena that initially appeared impossible or artificial, but later revealed natural explanations. This pattern doesn't invalidate the possibility that 3IATLAS represents genuine alien technology. It simply emphasizes the need for rigorous verification procedures and multiple lines of evidence before accepting revolutionary conclusions. The scientific method provides frameworks for evaluating such extraordinary claims. Hypotheses must be testable, making specific predictions that can be confirmed or refuted through observation. They must be falsifiable, specifying what observations would disprove the proposed explanation. Most importantly, they must be more successful than competing hypotheses in explaining all available data. Applied to 3IATLAS, The artificial origin hypothesis faces several challenges. It must explain not only the object's unusual characteristics, but also why those characteristics couldn't result from natural processes. It must predict specific observable consequences that distinguish artificial from natural origin, and it must account for the absence of obvious technological signatures such as controlled maneuvers, structured radio emissions, or impossible material properties. Current observations provide limited support for artificial origin scenarios. While 3IATLAS displays unusual chemistry and activity levels, these anomalies remain within the bounds of what might be expected from objects formed around different types of stars. The object follows a purely gravitational trajectory without detectable course corrections. Its coma and tail development proceeds according to standard cometary physics, responding predictably to solar heating. Most significantly, intensive radio monitoring has detected no artificial signals emanating from 3IATLAS. Multiple facilities worldwide have been searching for transmissions across broad frequency ranges using sensitivity levels that could detect even modest technological emissions. The continued radio silence either supports natural origin interpretations or suggests extremely sophisticated stealth capabilities. The absence of detectable radio emissions presents particular challenges for connection hypotheses, linking 3IATLAS to the original WOW signal. If both phenomena originated from the same source or represented components of a coordinated communication effort, we might reasonably expect the physical object to attempt communication during its passage through our solar system. However, the failure to detect artificial signals doesn't definitively rule out technological origin scenarios. Advanced civilizations might use communication methods we haven't yet learned to detect. They might transmit on frequencies we're not monitoring, employ modulation schemes we don't recognize, or use technologies beyond our current understanding of physics. Alternatively, probe missions might be programmed to remain silent, except during specific trigger events or geometric configurations. 3IATLAS might be waiting for its closest approach to Earth, its passage near the Sun, or some other predetermined condition before activating communication systems. These possibilities highlight the importance of maintaining comprehensive monitoring throughout the object's entire passage through our solar system. The current listening campaigns represent humanity's most intensive search for artificial signals from an interstellar visitor, using facilities and techniques that dwarf the capabilities available during previous encounters with Oumuamua and 2. The Green Bank telescope, with its 100-meter dish and advanced receiver systems, can detect signals thousands of times weaker than what was possible during the WOW signal era. The telescope's location in the National Radio Quiet Zone provides protection from terrestrial interference, while its steerable design allows continuous tracking of 3IATLAS throughout its passage. China's 500-meter aperture spherical telescope, FAST, contributes even greater sensitivity through its enormous collecting area. FAST can detect signals from distances spanning hundreds of light years, making it capable of eavesdropping on interstellar communications that weren't specifically directed toward Earth. The telescope's recent commissioning for SETI observations adds unprecedented capability to the search effort. The Very Large Array in New Mexico provides complementary capabilities through its interferometric design. Multiple radio dishes working together can achieve angular resolution impossible with single telescopes, potentially pinpointing the exact location of any emissions from 3I. The array's ability to separate signals from different directions could distinguish between transmissions originating from the object itself versus background sources along the same line of sight. International cooperation amplifies these capabilities through coordinated observations spanning multiple continents. As Earth's rotation carries 3IATLAS across different sky regions, facilities worldwide can maintain continuous coverage. This global approach ensures that brief transmissions or intermittent signals won't be missed due to telescope scheduling conflicts or local weather conditions. The search strategies employed by these facilities reflect decades of SETI research experience. Rather than focusing solely on narrow frequency bands like the hydrogen line, modern searches span broad spectral ranges from hundreds of megahertz through tens of gigahertz. They look for continuous signals, brief pulses, and complex modulation patterns that might encode structured information. Signal processing algorithms can identify artificial signatures even when embedded in natural radio noise. They search for frequency drift patterns that compensate for relative motion between Earth and 3IATLAS, modulation schemes that carry digital information, and polarization characteristics that might indicate technological origin. Time domain analysis represents another crucial component of the search strategy. Rather than monitoring only for continuous transmissions, the campaigns look for brief bursts, periodic signals, or transmissions that appear only during specific geometric configurations. Such intermittent signals might be easier to distinguish from natural background sources while requiring less power from potential alien transmitters. The negative results obtained so far don't discourage researchers who understand that even null detections provide valuable scientific information. Each non-detection places constraints on the power and sophistication of any hypothetical alien technology. The continued absence of signals either supports natural origin interpretations or indicates that any artificial systems aboard 3IATLAS are remarkably well concealed. These constraints become particularly significant when applied to the connection hypothesis, linking 3IATLAS to the WOW signal. If both phenomena originated from the same technological civilization, the failure to detect additional transmissions suggests either extremely sophisticated stealth capabilities or communication strategies operating according to principles we don't yet understand. The ongoing search campaigns serve multiple purposes beyond their immediate objectives. They provide technological proving grounds for next-generation SETI techniques, demonstrate international cooperation in addressing cosmic mysteries, and educate public audiences about the methods and challenges of searching for extraterrestrial intelligence. Educational aspects of the campaign extend its impact far beyond professional astronomy communities. Students worldwide are participating in data analysis projects, learning to distinguish between artificial and natural radio signatures. Public outreach programs explain search techniques and their significance, fostering scientific literacy and encouraging interest in space sciences. The 3IATLAS campaign also represents a crucial test of humanity's preparedness for potential extraterrestrial contact. The protocols developed for verifying and announcing any positive detections establish precedents for responding to future discovery. International coordination mechanisms prove that our species can cooperate effectively when confronting cosmic mysteries. Whether the searches ultimately detect artificial signals or confirm natural origin interpretations, they advance our understanding of interstellar communication challenges and refine our techniques for investigating anomalous phenomena. Each null result narrows the parameter space for potential extraterrestrial technologies, while demonstrating our growing capabilities for cosmic surveillance. The broader implications of studying 3IATLAS extend far beyond questions of alien intelligence. As the third confirmed interstellar visitor to our solar system, the object provides unprecedented opportunities to investigate planetary system formation processes throughout the galaxy. Its unusual chemistry preserves information about stellar environments radically different from our Sun's neighborhood. The carbon dioxide dominance observed in 3IATLAS's coma suggests formation around stars with different properties than our Sun. Higher mass stars burn hotter and faster, creating stellar environments where carbon dioxide might condense more readily than water. Such stars also evolve more rapidly, potentially ejecting planetary system materials before biological evolution can establish complex ecosystems. Alternatively, the unusual volatile ratios might reflect processing during the object's interstellar journey. Cosmic ray bombardment over millions of years could alter surface chemistry through radiolysis and other radiation-induced chemical reactions. Solar wind particles from the object's original star might have selectively removed certain compounds while preserving others. The mysterious nickel emissions without corresponding iron signatures provide additional clues about 3IATLAS's formation environment or subsequent history. These elements typically occur together in stellar nucleosynthesis and planetary formation processes. Their apparent separation implies unusual chemical or physical conditions that don't commonly occur in our cosmic neighborhood. Possible explanations include formation around stars with unusual metal abundances, processing in exotic stellar environments like the surfaces of neutron stars or the accretion disks of black holes, or encounter with interstellar phenomena during the object's long journey between star systems. Modern analytical techniques are perfectly positioned to extract maximum scientific value from 3IATLAS's passage. The James Webb Space Telescope's unprecedented infrared sensitivity reveals molecular signatures invisible to previous generations of instruments. Its spectrographs can detect trace compounds at concentrations measured in parts per million, providing detailed chemical fingerprints of formation processes. Hubble's high-resolution imaging capabilities document structural changes as the object responds to solar heating. Time-lapse photography reveals the evolution of surface features, the development of jets or active regions, and the rotation characteristics that inform models of internal structure and composition. Ground-based observatories contribute complementary data through their ability to maintain continuous monitoring. The Gemini telescopes, with their adaptive optic systems, can track morphological changes in the coma and tail with unprecedented clarity. Spectroscopic surveys document the appearance and evolution of different molecular species as internal temperatures rise during the object's approach to the Sun. This coordinated observational campaign represents a new paradigm in astronomical research, the intensive multi-wavelength study of rare, time-limited phenomena. Unlike stars or galaxies that remain essentially unchanged over human timescales, interstellar visitors offer only brief windows for detailed investigation before disappearing forever into the cosmic void. The data being collected will prove invaluable for studying future interstellar visitors, which are likely to arrive with increasing frequency as our detection capabilities improve. The Legacy Survey of Space and Time, scheduled to begin operations later this decade, will transform our ability to discover small, fast-moving objects approaching from interstellar space. Current estimates suggest we might detect dozens or hundreds of additional visitors over the next decade. This growing population will transform interstellar objects from individual curiosities into statistical samples that can reveal broader patterns about planetary system formation throughout the galaxy. We'll begin to understand which types of objects are commonly ejected during system evolution, what chemical signatures characterize formation around different stellar types, and how frequently genuine anomalies occur among the population of interstellar wanderers. The citizen science aspects of 3IATLAS research demonstrate how modern astronomy increasingly relies on distributed networks of observers and data analysts. Amateur astronomers with sophisticated equipment contribute valuable observations, particularly for monitoring brightness variations, tracking positional changes, and documenting morphological evolution of the coma and tail. Projects like the Unistellar Citizen Science Campaign have already begun collecting data on 3IATLAS from dozens of locations worldwide, providing temporal coverage that would be impossible for individual professional observatories to achieve. This distributed approach not only increases the total amount of data collected, but also helps verify observations and identify potential systematic errors. The involvement of citizen scientists also serves important educational and inspirational functions. Participants gain hands-on experience with astronomical research methods, while contributing to humanity's understanding of cosmic phenomena. Many amateur astronomers possess equipment and expertise comparable to professional facilities from previous decades, making their contributions genuinely valuable rather than merely symbolic. As 3IATLAS approaches its critical encounters with Mars, the Sun and Earth over the coming months, these various research efforts will converge to provide the most comprehensive study of an interstellar visitor ever attempted. Every spectrum collected, every image captured, and every measurement recorded will contribute to our expanding understanding of the cosmic environment we share with countless other worlds. The story of 3IATLAS and its potential connection to the WOW signal ultimately represents something larger than the sum of its individual mysteries. It embodies humanity's transition from passive observers of cosmic phenomena to active participants in a universe-wide conversation. Whether that conversation involves other technological civilizations or simply the exchange of information through natural processes, we are no longer isolated observers, but engaged participants in cosmic evolution. The search for extraterrestrial intelligence has evolved far beyond its early focus on detecting obvious radio signals from nearby star systems. Modern SETI recognizes that alien civilizations might use communication methods we haven't yet imagined, might disguise their activities to avoid detection, or might operate according to motivations and strategies completely different from human expectations. This expanded perspective makes every anomalous discovery a potential breakthrough. The WOW signal might represent a natural Mauser event, but it demonstrated that our instruments can detect powerful transmissions from interstellar distances. 3IATLAS might be an exotic natural comet, but it provides unprecedented opportunities to study authentic interstellar material with modern analytical techniques. More importantly, both phenomena force us to confront fundamental questions about our place in the cosmic community. Are we alone in developing technology and intelligence? Do other civilizations attempt to communicate across interstellar distances? What evidence would we need to recognize such attempts? How should humanity respond if we ever confirm that we're not alone? These questions extend beyond scientific inquiry into philosophy, ethics, and practical policy considerations. The detection of extraterrestrial intelligence would represent the most significant discovery in human history, with implications for every aspect of our civilization. The search itself, regardless of its ultimate outcome, expands our perspective and challenges us to think seriously about our cosmic significance. The correlation between the WOW signal and 3IATLS provides a framework for exploring these deeper questions while maintaining scientific rigor. Whether the connection proves meaningful or coincidental, investigating the possibility advances our understanding of detection methods, verification procedures, and international cooperation mechanisms that will prove essential for future discoveries. As we stand on the threshold of potentially revolutionary discoveries, we carry with us the accumulated wisdom of generations of scientists who dared to ask profound questions about our cosmic significance. Their curiosity has become our inheritance. Their methods have become our tools, and their dreams have become our continuing quest to understand our place among the stars. The technical challenges of monitoring 3IATLAS for potential artificial signals illustrate the complexity of modern SETI research. Unlike the relatively straightforward task of detecting continuous wave radio transmissions, contemporary searchers must account for a vast range of possible signal characteristics. Extraterrestrial civilizations might use frequency hopping patterns to avoid natural interference, compress information into brief pulses to minimize transmission energy, or employ spread spectrum techniques that distribute signals across wide bandwidths. Each of these approaches requires different detection strategies and specialized signal processing algorithms. Frequency hopping signals demand rapid scanning across broad spectral ranges, with pattern recognition software, identifying systematic frequency changes that distinguish artificial transmissions from natural radio emissions. Pulsed signals require high time resolution monitoring, with nanosecond precision measurements to detect brief bursts that might last only microseconds. Spread spectrum techniques present perhaps the greatest challenges for SETI researchers. These communication methods deliberately spread signal energy across wide frequency ranges, making individual transmissions appear weaker than natural background noise. Detection requires knowledge of the spreading codes used by the transmitter, or sophisticated correlation analyses to identify statistical patterns hidden within apparent randomness. The ongoing 3IATLAS monitoring campaigns employ all these techniques simultaneously. High-speed digital receivers sample radio frequencies millions of times per second, creating enormous datasets that capture every subtle variation in the electromagnetic environment around the object. Supercomputer clusters analyze these datasets in real time, searching for any deviation from expected natural emissions. The computational demands are staggering. A single hour of observations can generate terabytes of data, requiring processing power equivalent to thousands of desktop computers working in parallel. The Breakthrough Listen project has developed specialized hardware accelerators specifically for SETI signal processing, using graphics processing units and field-programmable gate arrays to achieve the massive parallel computing capabilities required for real-time analysis. Machine learning algorithms play increasingly important roles in these searches. Neural networks trained on vast databases of known natural and artificial signals can identify subtle patterns that traditional analysis methods might miss. These systems learn to distinguish between the statistical characteristics of thermal noise, astronomical sources, terrestrial interference, and potentially artificial transmissions. However, the application of artificial intelligence to SETI searches introduces new challenges alongside its benefits. Neural networks can identify patterns that human analysts would never notice, but they can also generate false positives by finding spurious correlations in random noise. Distinguishing between genuine discoveries and algorithmic artifacts requires careful validation procedures and human expert review. The search for optical signals from 3IATLAS adds another dimension to the monitoring campaigns. While radio transmissions can propagate across interstellar distances relatively easily, optical communications offer advantages for civilizations wanting to minimize detectability. Laser transmissions are highly directional, making them difficult to intercept unless you're positioned directly in their path. They can carry enormous amounts of information in brief pulses, and they're less susceptible to interference from natural radio sources. Optical SETI searchers monitor 3IATLAS for brief flashes that might indicate laser communications. These searches require extraordinary sensitivity and timing precision, since laser pulses might last only nanoseconds while carrying information equivalent to entire radio transmissions. Specialized photomultiplier tubes and avalanche photodiodes can detect individual photons, while high-speed electronics record their arrival times with sub-nanosecond precision. The challenge lies in distinguishing artificial laser signals from natural optical phenomena. Cosmic rays striking detector systems can produce brief flashes indistinguishable from laser pulses. Reflections from artificial satellites or space debris can create similar effects. Even statistical fluctuations in detector background noise can occasionally produce false positives. Overcoming these challenges requires multiple confirmation methods and statistical analysis techniques. True laser signals should display characteristics that distinguish them from natural phenomena: precise frequency stability, consistent pulse timing, or information content that indicates intelligent origin. They should be detectable by multiple independent instruments, and they should correlate with the object's position and motion in predictable ways. The infrared monitoring of 3IATLAS provides yet another potential avenue for detecting artificial signals. Advanced civilizations might use infrared communications to avoid detection by beings who primarily monitor radio and optical wavelengths. Alternatively, the object might emit characteristic thermal signatures from internal power sources or mechanical systems that would betray technological origin. Space-based infrared telescopes like the James Webb Space Telescope and Spitzer Observatory, before its retirement, can detect temperature variations across the object's surface with extraordinary precision. Natural comets display thermal patterns determined by solar heating, internal structure, and volatile sublimation rates. Any deviations from these expected patterns might indicate artificial heat sources or deliberately controlled thermal emission. However, interpreting infrared observations requires sophisticated thermal modeling to distinguish between natural and artificial temperature variations. Cometary nuclei can display complex thermal behavior due to internal structure variations, subsurface volatile pockets, or seasonal effects related to rotational orientation. Surface composition differences can create thermal patterns that mimic artificial heat sources. The multi-wavelength approach employed in current 3IATLAS monitoring represents the gold standard for SETI observations. By simultaneously searching across radio, optical, and infrared wavelengths, researchers maximize their chances of detecting any artificial signals while providing multiple independent confirmation methods. This comprehensive strategy also helps distinguish between natural phenomena and potential technological signatures. International coordination amplifies the effectiveness of these multi-wavelength searches. Facilities worldwide can maintain continuous coverage as Earth's rotation carries 3IATLAS across different sky regions. This global approach ensures that brief transmissions or intermittent signals won't be missed due to telescope scheduling conflicts or local weather conditions. The European Southern Observatory's network of telescopes in Chile provides Southern Hemisphere coverage complementing northern facilities. The Australia Telescope National Facility contributes additional radio monitoring capabilities, while optical observatories worldwide document any changes in the object's visual appearance that might correlate with radio or infrared emissions. This international cooperation demonstrates humanity's growing maturity in addressing cosmic mysteries. Unlike the early days of SETI, when individual institutions conducted isolated searches, modern campaigns involve coordinated efforts spanning multiple continents and diverse technical capabilities. This cooperative approach not only increases the probability of success, but also ensures that any discoveries would be independently verified by multiple research groups. The sociological implications of the 3IATLAS investigation extend beyond pure scientific considerations. How humanity responds to potential evidence of extraterrestrial intelligence will establish precedents for future discoveries and reveal fundamental characteristics about our species' readiness for cosmic contact. The protocols developed by the International Academy of Astronautics provide frameworks for verifying and announcing SETI discoveries. These procedures emphasize the importance of independent confirmation, peer review, and international coordination before making public announcements. The goal is to prevent false alarms while ensuring that genuine discoveries receive appropriate scientific scrutiny. However, implementing these protocols in practice proves more challenging than developing them in theory. The 3IATLAS investigations involve dozens of institutions worldwide, each with their own communication policies and media relations strategies. Coordinating information release across multiple organizations, time zones, and cultural contexts requires unprecedented cooperation. Social media and instant global communications add additional complications. In previous decades, scientific discoveries could be carefully verified and peer-reviewed before reaching public attention. Today's interconnected world makes it virtually impossible to contain information about potential extraterrestrial discoveries during the verification process. The challenge becomes particularly acute for anomalous observations that might indicate artificial origin, but don't provide definitive proof. How should researchers communicate about intriguing but inconclusive findings? How can they maintain scientific credibility while acknowledging extraordinary possibilities? The 3IATLAS case study provides valuable experience in navigating these communication challenges. Media coverage has ranged from responsible science reporting to sensationalized speculation about alien probes. Public reaction has varied from informed curiosity to conspiracy theories attempting to connect the object to various pseudo-scientific beliefs. Managing these diverse reactions requires clear communication about scientific methods, evidence standards, and the distinction between hypothesis and confirmed fact. Researchers must explain why extraordinary claims require extraordinary evidence while remaining open to genuinely revolutionary possibilities. Educational aspects of the 3IATLAS investigation serve crucial functions in promoting scientific literacy and public understanding of SETI research. Students worldwide are participating in data analysis projects, learning to distinguish between natural and artificial signals while gaining hands-on experience with astronomical research methods. These educational programs demonstrate how cosmic mysteries can inspire interest in science, technology, engineering, and mathematics. Participants develop critical thinking skills, learn about statistical analysis, and gain appreciation for the rigorous methods required to distinguish between genuine discoveries and false alarms. The involvement of amateur astronomers and citizen scientists in 3IATLAS research illustrates the democratization of astronomical investigation. Modern technology enables dedicated amateurs to contribute meaningful observations using equipment and techniques that were available only to professional institutions a few decades ago. Citizen science projects like the Interstellar network have already documented morphological changes in 3IATLAS's coma and tail, providing temporal coverage that would be impossible for individual professional observatories. This distributed approach not only increases the total amount of data collected, but also engages broader communities in the search for cosmic answers. The philosophical implications of investigating potential extraterrestrial intelligence through objects like 3IATLAS force us to confront fundamental questions about consciousness, intelligence, and our place in the cosmic order. If 3IATLAS were indeed an artificial probe, what would this discovery mean for human civilization? First contact scenarios have been the subject of extensive speculation in both scientific literature and popular culture. Most analyses focus on radio communications or obvious spacecraft encounters, but the possibility of discovering alien technology disguised as natural objects presents unique challenges and opportunities. An artificial probe designed to avoid detection while gathering information about our civilization would reveal sophisticated technological capabilities and strategic thinking. Such a discovery would confirm that we're not alone in the universe while simultaneously raising questions about the intentions and capabilities of its creators. The implications would extend across every domain of human knowledge. Biology would need to incorporate examples of alternative evolutionary pathways. Physics might reveal new principles or engineering applications we haven't yet discovered. Philosophy would confront questions about the nature and distribution of consciousness throughout the cosmos. Religious and spiritual traditions would face the challenge of incorporating extraterrestrial intelligence into their worldviews. Some theological frameworks already accommodate the possibility of life beyond Earth, while others would require fundamental reinterpretation of humanity's cosmic significance. Economic and political systems might experience disruption as established power structures grapple with the implications of advanced alien technology. International cooperation might increase as humanity recognizes shared interests in the face of cosmic neighbors, or competition might intensify as nations seek advantages from alien discoveries. However, these speculative scenarios assume definitive proof of artificial origin, which current observations of 3IATLAS do not provide. The object's unusual characteristics, while intriguing, remain within the bounds of what exotic but natural comets might display. The absence of obvious technological signatures suggests either natural origin or extraordinarily sophisticated camouflage capabilities. The burden of proof for artificial origin claims remains extraordinarily high, as befits discoveries that would revolutionize human understanding of our cosmic environment. Every anomalous characteristic must be carefully analyzed to determine whether natural explanations can account for the observations. This rigorous approach doesn't represent closed-mindedness or bias against revolutionary discoveries. Instead, it reflects the scientific method's emphasis on evidence-based conclusions and the recognition that extraordinary claims require extraordinary verification procedures. The ongoing analysis of 3IATLAS demonstrates these principles in action. Researchers are simultaneously investigating natural formation scenarios that might explain the object's unusual properties, while remaining alert for any definitive indicators of artificial origin. Spectroscopic studies continue revealing details about the object's chemical composition, comparing observed ratios to predictions from various formation models. Thermal analysis documents how the object responds to solar heating, testing whether its behavior matches expectations for natural cometary materials. Orbital analysis monitors the object's trajectory for any deviations from purely gravitational motion that might indicate propulsion systems or controlled maneuvers. Even tiny accelerations measured in millimeters per second could provide evidence of artificial origin if they couldn't be explained by natural outgassing processes. Radio monitoring continues across broad frequency ranges, searching for any structured emissions that might indicate technological systems. The searchers employ increasingly sophisticated algorithms capable of detecting weak signals embedded in natural radio noise. As 3IATLAS approaches its closest encounters with Mars, the Sun, and Earth, these various analytical approaches will provide the most comprehensive evaluation of an interstellar visitor ever attempted. The scientific community is prepared for any outcome from exotic but natural comet to confirmed alien probe. The psychological preparation for potentially revolutionary discoveries involves acknowledging both the excitement and the uncertainty inherent in scientific investigation. Researchers must maintain objectivity while investigating phenomena that could transform human civilization's understanding of its cosmic context. This balance between skepticism and openness represents one of science's greatest achievements. The willingness to consider extraordinary possibilities while demanding rigorous evidence creates conditions where genuine discoveries can be recognized and validated while false alarms are identified and eliminated. The 3IATLAS investigation, regardless of its ultimate conclusions, advances human capabilities for detecting and analyzing potential extraterrestrial technology. The techniques, protocols, and international cooperation mechanisms developed during this campaign will prove invaluable for investigating future anomalous discoveries. Whether we are alone in the universe remains one of the most profound questions our species has ever posed. The investigation of 3IATLAS and its potential connection to the WOW signal provides frameworks for pursuing answers while maintaining scientific rigor and international cooperation. The cosmos has presented us with two remarkable mysteries from the same region of sky, separated by nearly half a century but potentially connected by the vast scales of interstellar space and time. Whether this connection proves real or coincidental, the search itself represents humanity at its most curious, rigorous, and hopeful. As 3IATLAS continues racing toward its cosmic appointments, radio telescopes listen, optical instruments watch, and infrared detectors monitor for any sign that we might not be alone among the stars. The universe keeps its secrets well, but we have proven ourselves persistent students, ready to learn whatever truths await discovery in the infinite darkness between the worlds.